Work? Okay. Yeah, I suggest we start. And as announced, it's my pleasure to announce a talk, a small, short 30-minute talk as part of this lecture on numerical optimal control, which is given by Michael Neunert. And Michael did his PhD recently at ETH Zurich in the Agile and Dexterous Robotics Lab. And before, he has studied at ETH Zurich, where he did his master in mechanical engineering in 2012. And originally he's from Villingen-Schwenningen, where he went to school in Germany. Okay, so you have the word. Please put the micro on the shirt.
Thank you very much, Moritz. Very warm welcome from my side. As Moritz mentioned, I briefly recently graduated, and this is sort of a bit of my PhD work. So it's kind of my PhD presentation, which was in numerical optimal control. So I think it fits the topic really well. We come very much from the robotics side, so we come very much from the applied side of numerical optimal control. So I think it's kind of a two-way motivational talk. I think this gives you a lot of insight of where we actually encounter numerical optimal control problems. So it gives you a bit of the perspective of what you learn in this course, where you can apply this. I hope I can also motivate you that actually robotics is a cool subject to get into. So if you guys want to get into robotics, feel free to actually contact Moritz or me. I think we both have some contacts if you want to get involved. I have to say, probably our language is not always as precise and accurate as probably Moritz's language in the sense of like the nomenclature of algorithms. So I will try to make some references, try to be a bit more precise today that you can make the links to the lecture, otherwise interrupt me if something is unclear. So you probably, I'm not sure how much you know about robotics, but robotics holds that promise that robots can take over very complex tasks that a human worker cannot do or might actually be able to do, but not to the precision that a robot could do it. And here we have an example of a construction robot. This is only a rendering. This is not an actual picture, but this is from a project that we have together with architecture students at ETH, and they're looking into how to make new construction robots, new construction machines that can actually lead to new construction processes. So here we see a robot that is building a kind of a metal mesh that is then filled up with concrete, such that you can build newly shaped walls. I mean, there are also very other, I think, interesting applications for robotics that I'm not going to go into, but there's a lot, I think, where robots can be used in rescue robotics and other things. What we are focusing on is what we call agile and dexterous robots. So what we're basically looking at is mobile robotics, so all robots that are kind of able to move around and that actually work in unprepared environments. So we can see that already here on the construction side. This is not a standard industrial production line where everything is in a fixed place, organized, but you actually have obstacles, you have humans walking around. So, and I think this kind of sets the theme for numerical optimal control that is very reactive. I'll talk a lot about model predictive control as well, because we want to be able to react to changes in the environment very quickly. Now, what we're mostly concerned about is how to actually do the motion planning and control of the robot. So in this case, this actually means how can we actually make this robot move its tool in the environment very precisely. How does it get from A to B? But how can we also at the same time avoid obstacles, which can be humans or clutter in the environment? At the same time, we need to keep balance. We don't want to fall over. We want to be fast and efficient. So there are a lot of criteria that actually go into motion planning. And the interesting thing is they all happen at the same time. So it's a fairly complex problem that you can usually not tackle with simple heuristics, at least not if you want to be optimal. So this kind of sets the framework for any motion planner and controller that we want to set. And ideally, this motion planner needs to know about the dynamics of the kinematics of the robot, of the environment. And this already shows that actually this leads to kind of a model-based formulation for our motion planners. I'm going to talk a bit about legged and humanoid robots for the reason because I think here you can see the development of mobile robotics the best. So if you see, when we started out with legged robots, that was before my time, all of these robots were fairly simple robots with low degrees of freedom that were not very capable. And as you can see in the progression, now we have robots that are actually very versatile. They have many degrees of freedom. We actually also see a speed up in the development, so we have new robots coming out every year, and this actually poses a lot of problems because we have to be able to adapt our approaches to new machines, so we have to keep up with the hardware development on the software side. So I think this is very important for us. Now, I'm going to give you a brief overview of how control motion planning is tackled in the robotics world. So we're not all doing numerical optimal control, but in fact, there are various approaches and actually various, let's say, viewpoints on the same problem. So when we look at motion planning control, there's kind of the general feedback control community where you basically, which we also use, it's standard PID controllers or inverse dynamics controllers that actually just want to stabilize a certain set points. Then there's kind of the simplified model-based controls, where people try to find a simpler description of the robot dynamics, which allows them to actually solve optimal control problems or planners in lower state space. And then we have kind of the random sampling-based approaches where people draw random samples and try to figure out an optimal motion plan from these samples. And last but not least, this is something that I would call navigation and mission planning. So this is kind of like if you think on the long horizon, if a robot needs to fulfill a task on a construction site, pick up some goods, move them to another place, build, etc. So this is kind of the different also time scales that we're looking at. But what you can already see is that these different approaches, they're not necessarily always interlinked, and often you need a multitude of these approaches and need to combine them. And that usually makes it hard because the different views, the different descriptions make an integration really difficult. And at the same time, especially if you have, for example, simplified model approaches, you actually engineer a lot the problem. So you think about the dynamics, you think about your robot, and you think, what is a simplified model that I can generate for my specific robot? The problem with that is whenever you're giving a new robot, you start that process from scratch. So what we are asking ourselves really is how can we avoid re-engineering our motion planners and controls from scratch? So if we are given a new robot, how can we actually apply our existing techniques to that robot without re-engineering the whole problem? Because re-engineering costs time. So what's getting really popular is what I would call, what's often called offline trajectory optimization. This is nothing else than numerical optimal control, but often run offline. So that means you optimize here usually for minutes up to hours, and then you get a single motion for a robot. And obviously this is quite interesting because it's an optimal control approach. It allows you, once you give a model into your approach, to find a solution for that. But on the other hand, it's still a very slow and tedious process. You optimize for one motion, you execute it, and then you have to optimize again. So what we're looking into is efficient numerical optimal control. So the efficiency here just means that we're looking at approaches that we can run online or actually in model predictive control fashion. And as I kind of tried to indicate here a bit, these approaches can to some degree actually replace standard feedback and simplified model planners so that you have a nice integrated approach, and with the increase of computational power we can extend our time horizons. We have to say, there's a little asterisk here. The higher we go up sort of on that slide, the more these approaches are tested on real hardware. What I mean by that is feedback control, simplified model planners. That's something that we already find a lot in robotics that's actually applied on hardware, tested on hardware. And numerical optimal control is just something that is really starting off. So there are not many examples of where this is actually applied to physical robots. However, as mentioned before, ideally we can get away from, let's say, the task or platform or robot specific engineering towards more to algorithmic engineering, where we optimize our solvers, which then transfer to other systems and other problems. So this is really what kind of sets the theme also in this work. So here we have several different robots that we have at ETH in our lab. Top left, you see kind of a ball balancing robot as a service robot, so to say, if you want. This is a Haiku or quadruped robot. It's a walking robot. On the bottom left, we have the in situ fabricator. It's a mobile manipulator used for construction. And then we have unmanned aerial vehicles. And our goal is really we want to approach all of these systems with a single approach. And in this case, it's numerical optimal control, because once we have a model of all of these robots, we can ideally apply numerical optimal control, and we get a motion planner and controller out of it. So actually that sounds pretty tempting. So today's talk will be roughly separated into two parts. The first part will be where actually I talk about numerical optimal control in different formulations for different robots. In the second part, I'm going to give a brief introduction to our software framework. We're going to skip the localization part today because I think that's not so interesting for the audience here. Now, the first part that I'm going to talk about is numerical optimal control for rigid body dynamics, and I'm going to get into what rigid body dynamics are. The general problem we're looking at is basically a finite horizon optimal control problem. So we have a dynamical system, so usually that's an ODE, and then we have a cost function which encodes our tasks and constraints, and then we wish to find an optimal controller. Now, I think this slide is probably not as accurate as probably you've heard it in this lecture, but there are various approaches to numerical optimal control. I think this course is mostly concerned about the center, the basically nonlinear programming approaches. So where you have direct collocation, single shooting, multiple shooting. On the left-hand side, we have sampling-based methods. So these methods actually come out of the physics community, where you can actually have not random sampling based, but kind of semi-deterministic sampling, like path integral formulations. I'm not going to talk about these today, just that you know that these exist. And then on the right-hand side, we have differential dynamic programming, which in essence is very much related to kind of the centered and nonlinear programming approach. It's just a different view. These algorithms were kind of derived from an optimal control point of view, but actually end up in very similar formulations. So we have differential dynamic programming, which is kind of exact Hessian approach, single shooting, and then we have SIQ, which is basically single shooting with Hessian approximation and sparsity exploitation. So we're going to talk about this today. So in the context of this course, you can just think of these things as single shooting with sparsity exploitation and the Gauss-Newton backward sweep. Just briefly, kind of this is our viewpoint of the algorithm. What it does is we simulate the dynamics. That's where the shot comes in, the single shooting. We then linearize our system dynamics around the resulting trajectory, compute a quadratic approximation of our cost function. This gives us linear quadratic problems, and in this SIQ approach, we basically just use Riccati equations to kind of do that backward sweep, which then gives us an update for our control law, and then we repeat the process until we are converged. Now, this is mostly the approach that we've been looking at, and what we're looking at is applying these things to what I would call rigid body dynamics that are potentially in contact. So here you see a robot from the DARPA Robotics Challenge. This was one of the big robotics challenges that has happened last year, where a robot had to fulfill different tasks. Usually they used legged robots for that, so they had to drive a little car, they had to climb some stairs, they had to close a valve, drill a hole. And all of these tasks, and whether if you're drilling a hole or you're climbing stairs or you want to get into a car or drive a car, you usually are subject to contacts. And I think the contacts, is what really makes it interesting in robotics. I will get into details why contacts are kind of the crucial thing here. The other point is we're talking usually about rigid body dynamics. I will briefly describe what rigid body dynamics are, but it's kind of, we assume that our robots are all consisting of one or multiple rigid bodies that are linked over joints. That's kind of the essence of rigid body dynamics. So no matter if you have a walking robot, a flying robot, a ground robot, this assumption usually holds as long as all of our bodies are rigid. I mean, there's also soft robotics where your links are actually deformable, but what we are looking at is actually rigid links and rigid bodies. That makes a lot of your life easier. What I've written down here is the standard rigid body dynamics equation. So for your reference, this Q is basically the joint state. So this can be the state of your actual links. If you have a robot arm, can be the joint angles. It can also be, in the case of the walking robot, the position and orientation of the main body. So what you see here is that in this rigid body dynamics, it's a nonlinear equation with respect to your states, even though it still has quite some linear features. So it's not as gnarly as other nonlinear systems, but it's still a nonlinear equation. It's not a necessarily unstable system, so most rigid body dynamic systems are actually marginally stable, so that's good. So our kind of requirements on our solvers are not as strict as probably in other problems. So what we see basically here is the first term is kind of a mass matrix which describes where all the masses and the inertias. The second one is kind of Coriolis terms, that is kind of rotational effects. The G term is gravity terms that acts, so we have all bodies are subject to gravity. And then what we have on the right-hand side is lambda, which are the contact forces if we have them over the contact Jacobian. And then the tau is basically joint forces or joint torques that affect the system. Now, what we usually then have to do is, if you want to apply numerical optimal control to rigid body dynamic systems, we have to figure out what is actually our ODE, so what is the system dynamics that we present to the solver. And there I will just briefly talk about that there's not a single way of transferring rigid body dynamics to an ODE. There are several choices here that you can make. Again, this is where the contact problem comes back, because the contact problem can actually introduce quite some coupling. So I drew a little mock-up of a robot on the right-hand side, and what you see there, you see the contact forces lambda, and you see the joint forces tau that can potentially actuate this robot. And as you can see from the picture, already lambda is probably somehow a function of tau and vice versa, so they are coupled. This is already quite interesting, but then if you have a contact state here, we can actually see, okay, there's still somehow a coupling between lambda and tau and the other states, but now this coupling probably looks quite different because one of the feet of that little robot is actually off the ground. So what I would try to say by this is the equations actually quite change with the contacts and depending on how you model the contacts. So I'm just going to talk about this a bit from a broad perspective, but there are different ways of actually getting the contacts into your rigid body dynamics and then later into your numerical optimal control. So one simple way that you can actually go about is what I try to show here on the left-hand side is basically a contact model approach. So what you do is you take your rigid body dynamics equations and you add what is called a contact model. So given a state of the robot, what are the contact forces that my robot will experience? So what you can, for example, do is, I'm going to talk about this in a second, is if your foot is on the ground, it penetrates the ground, you have sort of a virtuous spring that pushes your foot out of the ground again. So it's kind of a way of modeling contacts and to come up with a force law depending on the state of your robot. The second thing is kind of a hybrid or projected approach. Is very popular if you assume your contacts are perfectly stiff. So given a configuration of your robot, you have different models. So you have one model when the robot is not in contact, and you have another model when the robot is in contact, and you can actually have even more than two. You can have a multitude of models. So you switch your system dynamics depending on how many contacts the robot currently has. The third one is actually, we just take our rigid body dynamics, so just kind of the physics of our robot without contacts at all, and then we enforce the contacts over the constraints. And I will also talk about this. We'll actually start out with this formulation to just give you an intuition of what it means. So what you see here is we first define our state. Our state consists of several elements. The first element is what we call the base pose and base twist. So this is the main body of the robot. Could be in a humanoid, the trunk, the chest, which has a certain position and orientation. And then we also have the different joint positions of all of the limbs. And we define this in our state. And then our dynamical system, our ODE, is basically the rigid body dynamics that I had shown before, just reformulated. And then we choose our control input as our joint torques and the contact forces. Now this is a bit weird because, as I mentioned before, these are not independent variables, right? Given some joint torques in a given state of the robot, you have certain contact forces and vice versa. And what we actually have to do is we have to add an additional constraint. So I tried to explain it a bit in the top right corner. And there you see, for example, this could be a foot or a hand or whatever of the robot that can establish a contact with a wall. And what you can say intuitively is that if I have zero distance to the wall, so I'm in contact with the wall, then I can have a contact force lambda. But if I'm away from the wall, so I have a distance, then I cannot have a contact force. That's just kind of intuitive physics. So you can just say, okay, this product of distance times contact force has to be zero. And this is actually a constraint that you can add to your optimization problem. However, this is not the nicest constraint because it can make your problem quite non-convex. There's an alternative approach, and where we say, okay, over time, we know a certain contact sequence. So we know we introduce this binary variable C, which tells you, okay, if I want to be in contact, that is 1, and if I don't want to be in contact, that's 0. And what this allows us to do is to basically separate the constraint, saying, okay, if we're in contact, I can have a contact force, but if I'm not in contact, there should not be a contact force. Now this seems, it's kind of a mixed bag here. We have to actually pre-specify our contact sequence, which requires some external knowledge of what your contact sequence should be. The good thing is when we talk about walking robots, for example, contact sequences are equivalent to gait patterns. So if you think of a walking robot, there are different gaits like walking, running, trotting, etc. And we have a lot of expert knowledge from biology what these contact sequences are. Now, we basically apply this approach to our hydraulic quadruped robot HiQ. So this is a fully torque-controlled hydraulic robot. So we have force control in all of the joints. It's a very dynamic, very agile robot. It also weighs 80 kilos, so it's quite impressive. It's quite a beast also to run experiments on. But it's a very nice platform to actually do control. So we started out in simulation, and as I mentioned, we have some intuition from biology of what our contact sequences are. So we actually optimized over different gait patterns, so over trotting, over walking, over galloping. So we would just kind of set the contact sequence, and then we let our optimizer actually optimize over the whole motion. So this is all the output of the numerical control approach. We give in the contact sequence and it figures out quite some interesting gains. Now, I guess this shows a bit the power of numerical optimal control, because if you would have to design these gates by hand or with a heuristic, this is actually very difficult to design with the classical approach, because what people do in classical approaches, they have some cyclic behaviors for the legs, and then they've tried to figure out how to get the cyclic behavior of the leg together with a base controller. So it's really difficult to get right if you have kind of a classical approach. So this is where numerical optimal control really helps us. Now this robot that I just introduced is not a humanoid robot, it's a quadruped robot, but we can also make it walk on 2 legs. This is something we could never run on hardware, but just to show that this formulation just directly transfers to other descriptions as well. Now, we can also run some of these things on hardware, and I can get into details why we cannot run all of this on hardware, but we can actually make our robot also trot a bit in the lab, and we'll have some nice examples later on. So what we've seen here is basically these were pre-specified gates. So we have decided what are the contact sequences that the robot should follow. But in some occasions it would be actually nice when the robot could actually discover the contact sequences and the gate patterns by itself, because depending on the situation you might not always figure out what is the best gate or what is the best contact sequence, especially if it's not kind of a monotonic gate. So here we come back to the first formulation where we take our rigid body dynamics and we actually add a contact model. So we give our numerical optimal control algorithm a system which includes the contact, so it can reason about contact, so it knows what a contact is, and you can leverage via gradient computation the knowledge about the contacts. So if we go back to our formulation, we have the exact same state representation, the exact same dynamics. The only difference is now our input is only the joint torques. Now the question is, what is our contact force lambda? Our contact force lambda is now a function of the state. So given the state that my robot is in, we can derive a force law, which are the forces that act on the robot. So what we basically do is we try to figure out what is where's the end effect of the foot or the hand of the robot with respect to the ground, and we introduce some virtual spring dampers that basically avoid or try to prevent ground penetration. So it's a simplified contact model. It's what we call a soft contact model, so there can be a bit of penetration, but usually we set these springs to really stiff, so you actually don't get so much ground penetration. So what we can do now is we can actually run our numerical optimal control algorithm basically just without pre-specifying any gate sequence. So we just, via constraints or costs, we just say, okay, walk 2 meters forward. And what happens is that actually the optimal control approach figures out some gate sequences. So what we did here is we just told the robot, okay, walk 2 meters, get to a point 2 meters in front where you started. But we didn't say, oh, use a walking gate, use a trotting gate. But these gates are basically an outcome of the numerical optimal control approach. And the nice thing here is, even if you're not in walking robots, you have an intuition what an optimal gate is, because we see it in nature. We see some gates in nature, and we assume these are optimal. So if we see a trot emerging from a numerical optimal control approach, we have some intuition that this might be actually close to an optimal solution. If the robot would be limping quite asymmetrically, you would probably say this is by far not optimal. So here this is actually very nice because, again, we don't have to handcraft these gates, but they are a natural outcome. We can also do some other stuff, so kind of balancing on 2 legs. Or again, this is very interesting how the robot figures out a way to get up on his hind legs. And the nice thing is these are all kind of just changes in the cost function. So we get very different gates, very different behaviors just by changing our cost function. Now, I'm not going to go into much detail, but what we do is basically when we execute this on hardware, we usually add a tracking controller that tracks these trajectories that we get out of the numerical optimal control algorithm. And what this allows us to do is to execute some of these motions actually on hardware. So here we see a little squat jump. And then we will also later see, I think this is the most interesting part, which will be a rough manipulation task. So what we call rough manipulation is when our robot actually has to manipulate its environment. So here the goal is to push over a wooden pallet. You see that here. So the robot is standing in front of the pallet and is supposed to push over the pallet. And the interesting thing here is we don't specify the contact timings or the contact. So we perturb the robot once with the pallet below the front legs, once below the hind legs, and we have exactly the same cost function. And what we see is that the lift-off point or the lift-off time is actually different in the two examples. So even though we run the same algorithm with the same weighting, we actually get different contact timings. And I think this is the power of having an approach where the optimal control approach can actually reason about contacts. We see that here again in the picture. So we have the same robot but perturbed differently, and this is a screenshot taken at the same time. We see the left one already lifted off the leg while the right one didn't. And then in the bottom we see that both robots have their foot up in the push position at the same time, because this is what we specify in the optimal control approach. We basically say we specify the timings when the push should happen, and the rest, when to lift off the leg, this is left free for the optimizer. So this is maybe also interesting for you. What we see up here is kind of the convergence of the algorithm. So we have the normalized costs over the iterations for all of the different gate patterns that you have seen. So usually most of these gate patterns and motions, they come out of our optimal control algorithm within 20, 30, 40 iterations. So it's something that works reasonably fast, and this is actually where I'm going to get into next, which will be kind of how we can run these as model predictive control. So what you've seen before were all pre-computed trajectories and then executed on hardware. We don't do classic model predictive control. In model predictive control, you solve your optimal control problem at each control cycle, and you just apply the very first control input. Unfortunately, our solvers are not fast enough, so what we do is we solve the optimal control problem, we get a trajectory, and then we apply the first several inputs of this control trajectory and add a little tracking controller around it. So it's not classical model predictive control, it's more receding horizon planning, if you want to say so. We applied this to different platforms. One is the wall balancing robot. It's probably the least exciting example, but it allows us to basically disturb the robot, drive it around with this optimal control formulation. The more interesting approach is, I think, the model predictive control on this flying robot. So here the goal for the robot is to reach the other side of the room, and we assume there's a high-level planner that tells the robot whether to go through the left window or through the right window, and this planner can change its mind. So sometimes it says left window, and while approaching the robot, the window, the robot actually has to fly through the other window. I think what you see here is kind of the quick replanning. So here we are running a model predictive control with a time horizon of up to 6-7 seconds, and we solved the optimal control problem in a couple of milliseconds. So it's a fully dynamic trajectory that we see here that gets planned in several milliseconds. So here I think there's also a nice example of motion planning and control combined. So we're planning the motion and controlling the robot with the model predictive control approach at the same time. Now, also, this is our simulation environment, so we can actually run our model predictive controller on our walking robot as well. And here you can actually see it a bit trotting with this model predictive controller. So here we have a time horizon of 500 milliseconds, rather short. We run it at MPC rate of 100 hertz, and this also translates to hardware. These are very early results. So the video quality, unfortunately, is not the best, but what we see here is our robot doing the trotting gait, and we will poke the robot a bit with a stick. And what you can see is then that the gait pattern actually changes. So you will see that the right hind leg at some point will stop kind of lifting off the ground, because the robot can reason about the context and realize, okay, I'm getting pushed. It's better now if I don't lift off my leg. So this is kind of the benefit of having an approach that can reason about contacts, while if you would just do a standard trotting gait and you get pushed, it will still lift off the leg. Yeah, so this brings us towards the end of the talk. So if you guys have any questions, I'll be happy to answer them. And yeah.
Because of course the spatial dynamics is very stiff.
Yes.
I wondered if you had some problems using what simulation method did you use?
Yeah. It is a big problem. So the biggest problem, as you said, is stiff equations, very stiff equations. So what we have to do is use short integration time steps, and then we use a symplectic integrator. So it's in between an implicit integrator and an explicit integrator. So what it does in kind of the physical sense is you integrate your velocities first, and when you integrate your positions, you use the updated velocities, while an explicit integrator uses the old velocities to update the position. So it's not as expensive as an implicit integrator because you don't have to actually compute your sensitivities. So it's at the cost of an explicit integrator, but it's numerically a bit more stable. It's quite common we get a lot of inspiration also from physics engines used for computer games and animation, because they have the same problems, and they usually use this kind of symplectic integrators.
Just to add up to this question, did you try an implicit integrator once?
No, we have never tried it.
I think still these dampened springs, they call maybe for a real implicit integrator.
I think there could be a benefit from this. I think at some point also the dynamics become very fast. So probably with an implicit integrator you could take quite big time steps. But then the question is really, do you want to have these big time steps, or do you prefer also for the control inputs a shorter discretization? Yeah.
So coming back to the models that you use.
Yeah.
So we have this different model classes, and I'm not sure. I understood the way that you said, like, we have a different model for every combination of contacts, like the contact model. So
yeah. So I think you're referring to the middle, to the left one.
To the left one.
Yeah. Okay. So in the left one, it's fairly easy. So you have your dynamics of the robot that there's not a contact, and then you have the rigid body dynamics equation where you have the term of the contact forces, and then you compute this term by taking the state of the robot, figuring out what is the penetration or violation of the contact, and then you have a repelling force that pushes you out of the contact violation. So it's kind of a
so it's one big model, and these contact forces are figured out along the way. You don't sort of swap out the model.
No, yeah, exactly. It's one model. It's kind of continuous. This is also why our springs and dampers are kind of smoothed out. I can maybe show you that quickly. So you see, so basically what we see down here is this is the border of zero ground penetration. So if you're above the ground, you obviously don't have any force, and then once you start penetrating the ground, you smoothly increase the contact force. And this is actually for the reason of computing gradient information, that you always have kind of a smooth function that is not discontinuous. So yeah, it's a basic.
So if you really run those plans on hardware,
Yeah.
has there some state estimation or something to be done online so that you can always update the plans, or really does that work with most of the time, or does it possible?
No, so actually, so this is, let me quickly pull that up. This is what we see actually here. So what we have is actually quite an estimation pipeline. So we first, in a case of a walking robot, we have to estimate, are we in contact or not? That's what we call a stance estimation. Then we have a base estimation. So we have joint sensors in the robot, but we don't know what is the position, the orientation of the base. So we use the joint sensors and the stance to figure out what is our position of the base. and then we also have to estimate the ground inclination. So it's kind of a whole estimation pipeline, and we also have to have a whole control pipeline that actually tracks these trajectories. Of course, if we run it in MPC fashion, we don't need the feedback controllers, we get rid of them, but in most of the cases we actually have feedback controllers on the joint level as well as on the base level. Yep. Yeah. So usually we run it like the control discretization is 100 Hertz. So we have a very fine discretization, so 10 milliseconds discretization. So this is actually an unconstrained problem in this case. So our solver is currently unconstrained, so that makes it a bit easier. But I think it's a mixture of Gauss-Newton approach, which like sparsity exploitation, which SAQ does kind of by default. So I think this is why we like this algorithm so much, because we're not the experts in designing the solvers, but this SAQ type algorithm exploits the sparsity automatically, so you get a very fast solver. Yeah, I mean, technically, I think for just stabilizing the robot, you wouldn't need such a long horizon. So when we just hover, actually here the horizon, you see that in the top right corner, you see the planned trajectory, and you see how the horizon shrinks. So for just hovering, you need a very short time horizon of a couple of milliseconds. But we actually want to plan the whole trajectory just in a robotics setting. If this was a real room, you probably would need to consider, oh, I have to brake after passing through the window to not crash into the wall. So the time horizon is fairly long. However, it possibly does not have to be that long for stability. It's just, if we can, why not? Yeah.
So for that same problem, the OCP was solved not on the hardware, but on a computer or somewhere else.
No, so in this case, this is the model predictive control. It is actually computed on the UAV, but it has an Intercore i7 on board, so it's a fairly capable computer. But it's solved on the robot itself.
Is that what the other ones you solved?
So all the model predictive control is solved online. With the quadruped, the computer is physically off the robot. We could strap it onto the robot. That would be just an engineering exercise of taking the computer and mounting it. But technically, all of our model predictive control approaches are obviously run online and on hardware that could potentially go on the system. Yeah.
But on the other one, like where you use constraints.
Yes.
So you give a fixed gate sequence.
Yes, that's correct.
And then you use like a time transformation or something to be able to decide how long one step will take.
No, so we are actually using, so the contact sequence is actually in time. So you could also use it kind of in, you can solve it in phase space and then later on figure out the timings, but here it's literal time.
And then related, like engineers also try to get, from my understanding, why the contact forces are controlled.
Yeah, so this is kind of a trick to get around the contact problem. So either the contact forces, you have somehow a physical law that describe your contact problem, or you switch your models, right? The third one is you say, okay, I allow my optimizer to freely choose torques, joint torques, and contact forces. Then I can actually get unphysical behavior, so I can be in the air and have a contact force. So that's something you don't want, so you put the constraint in that there cannot be any forces while you're in the air. So
The actual magnitude of the contact forces can still be unphysical, right?
So I mean the dynamics it's make sure that they are kind of physical, right? You can have two high contact forces, but then probably your robot would fly away. So one thing we cannot capture with this approach, what's kind of unphysical, is we cannot capture impacts. So usually when you have a contact, you might actually see impacts which lead to discontinuities. So we don't capture that part. But yeah.
I have one final question.
Yeah, so what we so our lab background also from my boss Jonas Buchli is also reinforcement learning for policy learning. So you directly learn the policy, and then there are two ways to do that. You can either learn the policy in simulation, which then basically boils down to numerical optimal control without explicitly computing the gradients. You estimate the gradients from your sample. So this is why I say, okay, this part of research, then you might as well do numerical optimal control and compute your gradients if they exist, because then you converge faster. We did some policy learning on the actual robots. There are two problems with that. First of all, a lot of these approaches in policy learning, they have an exploration. So you randomly perturb your policy, and you don't want to give random policies onto your robot. That usually ends up in nasty crashes. So that's kind of one restriction. So you have to do kind of safe learning, which is a whole research topic by itself. The other problem is it's very tedious to actually gather sufficient samples, because you have to do a lot of rollouts and you always have to reset your system. And usually we're not done with 10 or 15 samples, but to learn something more sophisticated, a bigger policy with more parameters, you need hundreds of trials, and that just takes ages.
Okay, that's concluding remark. I thank you very much again.
Thank you, Moritz.
Just to thank you, and then have a break of 10 minutes. So thanks a lot. Okay, so we continue with the usual part of the course, and I would like to make a few announcements about the organization of exercises and projects and lectures. So as you have seen, the current exercise is a bit too early for what we have taught until now, and the deadline for this exercise should actually not be next week but only the week after, so that we can recover on the teaching side. And the reason for this is twofold. I mean, first of all, you should get some time to think and start thinking about projects, if you like. Yeah? So as you remember, some of you, or hopefully all of you, should have time to do little projects which replace, so to say, the work that you do on exercise in the last few weeks. And these need not be very elaborate projects, but it could be, think of one extra exercise sheet which you formulate yourself. You think, I would like to optimize the system, or I would like to try this algorithm that we didn't try yet in the exercises. So this is like a self-chosen exercise in principle. So this is what a little project is. Of course, at the end, we would like to have a public presentation of the projects and also a short report on these projects. But please don't think of them as being a full-fledged research project. It should be a bit less than a research project, yeah? The shorter, the better, so to say. So that's what I wanted to say on the projects and on the exercise. And on the lecture side, I wanted to say that next week we will have only the Monday lecture. Yeah, so there will be only a lecture on Monday. There is no lecture on Wednesday because and everyone is actually in my team at a conference at Toulouse. But the exercise so Monday next week we will have a class, and also Tuesday there will be the exercise session. It will be guided by Dimitris Kouzoupas, who fortunately is here next week, and he will be available for questions about projects. Yeah, so if people want to go to a project. On the other hand, maybe I could directly ask if there's no one coming next Tuesday. We could ask it, and then we don't need Dimitris to go there. So maybe I will ask this on Monday. Or is there some people that probably will participate next week on the exercise as usual, so to say? Yep, as usual. Good. Okay, wonderful. Yeah. So there is some interest. Yes, exactly. So wonderful. So that's a way for feedback. Thank you, Dimitris. And we start teaching. And maybe, okay, there's a question. Yes. Some technical problems. They have some technical problems at Prüfungsamt that needs Okay. They don't know the error. Okay, that's embarrassing, but fortunately not for me now. But okay, sorry, but still I feel ashamed also. Okay. So basically, everyone who wants to participate in the exam, and please write also an email to the Prüfungsamt of the technical faculty. Maybe put Andrea and CC and just say, I want to participate in the exam on numerical optimal control. I think it makes their life easier if you indicate the number of the class, this number in his in one, which I forgot, but you can copy it into the email. Maybe why don't you write such an email and put Andrea and CC, he forwards the email to everyone, and then, it's like a mass petition. Yeah, okay? How to subscribe to the projects?
It was a week ago, at least. I couldn't find it.
So you couldn't find the projects yet?
Yeah, it wasn't.
Yeah, I mean, just do them somehow. We will. This is not an exam, so it's less formal. I think we will be able to manage you to get the credits for that.
Maybe somebody should deal with the examination office. Because we also can't do it.
Yeah, I mean.
They should take some sort of.
No, they had a lot of maternity leaves. That's the problem. Yeah. Okay. Good. Yeah. Let's continue with mathematics. Okay. Just a little bit of mathematics, so that we don't get out of this. So maybe to just recall what we did last time, we derived the collocation equations that basically lead to a form of implicit Runge-Krutter method, and we didn't specify yet how this could be used, but basically an implicit Runge-Krutter method solves this nonlinear equation system in each step and is therefore more expensive per step, but it can take larger steps, and in many cases it is the most competitive variant. I should also say that it will come back at the end of the lecture in the direct collocation method. So that's where collocation equations pop up again. But there they will not be solved by the simulation routine, but they will be fully simultaneously solved by the optimization solver. So it's relatively straightforward to imagine already how it will look like, but we will go through it later. So what I want to do today is cover one or maybe even two, but I think probably one of the general knowledge topics that I think you should take with you when you do a numerical optimal control, even though we will take them very, very briefly. So the first one is called the Hamilton-Jacobi-Bellman equation. I would like you to know what it is, what it computes, and how it's related to the rest of the lecture. Yeah? So, and the second one is the Pontryagin minimum or maximum principle, PMP, which is also something that is very popular to know about in optimal control. So these two things I will treat relatively short, but I hope that you get these basic ideas from this presentation. And I will keep it rather on shallow, let's say, but I will try to explain those things that I do okay, so that you can accept them. So we rather look at a very simplified problem, and this is chapter 11 about the Hamilton-Jacobi-Bellman equation. So, and I will try to derive it from what we know already, namely from dynamic programming. There are other ways to do it, but I like that most. So the problem we want to solve is a problem in the simplest setting of a fixed time horizon, where we have some Lagrangian cost function, some Meyer term at the end, which depends on the terminal state. Then as constraints, we have an initial value constraint that just says that the trajectory should start at some fixed value x0 bar, and the trajectory itself should satisfy this equation. And I omitted the time index, but of course, implicitly, we should think that this constraint should hold for all time points. So that is the problem we would like to address in this section. And we do something that I would never do in practice, but we do it for the theory. So I want to basically transform this with an Euler discretization. And I do this because then I can later on I will let it go to 0. And then an Euler integrator, because it's just the simplest, it's not the most efficient, right? But it's the simplest way for writing down these equations. Everything else will not add any value to the derivation of the equations. So after the Euler discretization, I will actually just transform this whole problem into a finite dimensional optimal control problem, right? So I will get, and I will do some notation, and maybe I should make sure that I have this notation clearly explained. I actually identify a few things, and I will give the same names because I don't want to always introduce new names, so it should be a bit confusing maybe, but I will make maybe the symbols here at the top. Here I will have tk, x of tk. I could use it xk, so then I don't have to write so many things. Maybe I should also say that the tk is like the k times h, so the time step at time k times h. And of course, the time horizon is divided into n steps, so I will have n here, and n is actually t divided by h, right? So it's a number of time steps. So h should be, n should be an integer number usually. So we go with n to infinity or with h to 0. And yeah, let's just write this optimization problem. So then our optimization variables are the x and u trajectories. So like in discrete time optimal control, we got now a sum. I start summing at k equals 0. I stop at n minus 1 like usual. And then this is transformed with a simple Euler integration, or in this case it would just be a Riemann integral, right? So it's h times L of xk and uk. That is the replacement for the integral. And then I have here e to xn. And my continuous initial value constraint is replaced by this one. So my first state should be starting at the trajectory. And now this one, I can write it down in different ways. Maybe let me directly, we will use this form. So I will say xk plus 1, minus xk, minus f of xk, here I put the h already. F of xk, uk is equal to 0 for k from 0 to n minus 1. So if you compare it with this equation, basically you could divide this whole thing by h. Then you would have the difference quotient here that approximates the x dot. But from another point of view, we basically have, and maybe I make brackets around this, and I put a plus sign here, then it's the same, right? This is like one Euler step in order to approximate the dynamics of the system. Like the simplest integration rule, you could say. So in a sense, you could say this is multiple shooting with one Euler step per multiple shooting node, if you want to say so. Okay, so now we have transformed this system into a discrete time system, and we could formulate the Hamilton-Jacobi-Bellman equation. So maybe I should give already a headline, and I give it here. So it's actually now 10.1. It's dp in continuous time, so to say, what we want to derive. And that is actually the Hamilton-Jacobi-Bellman equation. Is there some question already, or no? Good. So let's just write down the dp equation for that. So remember, what does dp mean? dp introduces cost-to-go functions for each time step, so we will have j0 up to jn, these functions, and we know already that at the end, jn of xn will be equal to e of xn, that's the terminal cost. So this thing is clear. Then we have the dynamic programming recursion, which says that the jk, for k starting at n minus 1 down to 0, we know that this at some value x is given by the minimum over all u of, now we take the stage cost, which in this case is just h times L of x and u. This is the immediate stage cost plus the cost to go at the time step afterwards, which is then j k plus 1. And we insert here now, and I directly insert the dynamic system here, namely this step, which is xk plus h times f of x and u. Sorry, this is just an x. It's this x, and this u is also without an index. The only index is here actually the k. So that is the Hamilton-Jacobi-Bellman equation. Sorry, this is not. This is just dynamic programming as we know it. So we have a terminal condition, and then we propagate these functions j backward in time. And if you think of it now, this time index 0 here is somehow tedious, so we should identify something on the continuous time side. And what I will now identify is what I have here, jk of x. Yeah? I will also just use a different notation. I mean, k stands for the time index, which is corresponding to this time point, right? So I will actually identify this with something where I add a second argument, which is the time. So I will actually also use this notation. And I will assume differentiability of this function, which is, of course, a very strong assumption. But if you assume it, then, of course, you can do a Taylor expansion of this part of the function, which you would find reasonable, because at the end we want to make the h go to 0, right? So let me do a Taylor expansion of what we have. I mean, I just rewrite this equation from top now in this new form. So what I have is j of x and tk, some t, I call it still tk, and that is now the minimum over all u of h times L of x and u. So this is all okay. And now here I do a Taylor expansion of my j, and of course I use already this time index. So what I will have is j of x comma tk. That's the time, the derivative with respect to, well, actually I will do a Taylor expansion at both time direction, and maybe I should first write down this in the new notation. This will be j of x plus hf xu, right, comma tk plus 1. Now I do a Taylor expansion both in the x direction and in the t direction, so this is a constant term. Then there comes extra terms. One is now the derivative in the x direction, so that's the gradient of j in x direction at the point x tk, and then this thing multiplied with the step that I do, namely f of x and u. And because this was depending on h, right, I put the h just in front of it because there was an h. And then I have the second part, which is now the time step here, but we know that the time points are 1h apart, so I can also just put an h here and then say this is like times dj by dt, also at this point x and tk. So until now I hope you agree that this is a normal Taylor expansion and nothing special, and it will actually go on as simple as this. So what we will now do is we will just collect all terms which, I mean, everything that doesn't depend on u, we can also just move to the left side. Interestingly, this j and this j will cancel each other. This thing doesn't depend on u either. This depends on u and this depends on u. So let's leave them on the right side. And what we will get is there's a minus h dj dt at x t, and maybe I put the t already. I identify t and tk because it doesn't matter now anymore which point we are. And I collect everything else on the other side. So I have a minimization of, and I put the h already out because there's everything now depending on h. A minimization of Lxu plus, and now I put here the gradient of x, j, x, t transpose times f of x and u. And this is, of course, what we need to minimize over. There's a question.
Yes. For the time derivative, where does the h come from? I understand
Yeah, okay, I will explain it. So, tk plus 1 is k plus 1 times h is tk plus h. Yeah? So that's where the h comes from. It's just the difference between two time steps. So I should somehow put a picture. So this is the continuous trajectory, right? Continuous controls, maybe, whatever. And this is 0, this is big T. And I now introduce a time grid. And this would be tk plus 1. And there's a time step h between all of them, because they follow this definition. So it's an equal grid. So it's a very brutal and simple discretization. Euler, one grid, no adaptivity, nothing. It has nothing to do with numerics. I just want to derive an equation. And therefore, it's okay. So now I see that the h is there on both sides, so I can remove it. And I get an equation which is already actually the Hamilton-Jacobi-Bellman equation. Usually one writes it slightly different, and one introduces a function that is this function actually. One will call this thing h of x and nabla x, j, and u. And my definition of this is called the Hamiltonian function. And it is for any x, lambda, and u, it is defined to be an Lx u plus lambda transpose f of x and u. And now if this lambda is not accidentally called lambda, it will have to do a lot with the adjoints from before. You might guess it already, because here I have the gradient of the value function. But at the moment it's just some variable that I just put there for this argument, and then I can obviously write this equation here in that form. And so my Hamilton-Jacobi-Bellman equation is actually the equation that says minus dj dt is equal to the minimum of h of x nabla xj and u, the minimum of u. So this is one way to write it. There is even another way to write it, and this is by defining another thing that I could call the minimized Hamiltonian. And the minimized Hamiltonian, you could just define it as a function of x and lambda. And it's the thing that already minimizes over the u. So I give it another name, h star. So if you minimize the Hamiltonian over u already, then you get this, then you don't need the u anymore. And in many cases, you can actually compute this explicitly. And then your HAB equation just looks like this. So even making it simpler. Okay, so what we observe, of course, is that this is a PDE, partial differential equation. It lives in which space? I mean, its domain, if you would like to plot it, on the one hand, there is, of course, state space. In the other direction, there's time. Time goes from 0 to big T. We know that there is a terminal condition. At the end, it has the cost to go function should satisfy that it's equal to the terminal cost. And then it defines basically a backwards evolution. That's what we would expect from dynamic programming. You could pictorially say this is the meaning of this minus sign here. So we basically go backward in time, but of course a minus sign is just a minus sign, so we shouldn't overestimate what it means. But numerically it is really, if you would solve it, you would start with the end, and then you would somehow propagate it to the end, to the front, by basically noting that the time derivative of your function j is given by this expression. And so when you know the spatial derivative of your j, then you can compute the time derivative. So it's a bit like a diffusion equation. Of course, it's not a diffusion equation. It's a Hamilton-Jacobi-Bellman equation. It's a more complicated equation. but you could think of it as something that evolves backwards and changes somehow the cost over time. Of course, it's not so different from dynamic programming. The difference is that now time is really continuous. Yeah, that's the main difference. All the same difficulties appear, like the curse of dimensionality. If this x is not one dimension, but 2 or 3 or 4, then it's a PD in a 4-dimensional space, plus time. So it gets very quickly impossible to store even the data for that. Yeah. So that's the Hamilton-Jacobi-Bellman equation and the minimized Hamiltonian. Very quick. So I will not go into details. I just want to say that there is lots of people that try to solve these. Last week I was on this workshop on numerical optimal control, where half of the presenters were actually working on these approaches to solve these Hamilton-Jacobi-Bellman equations, and none of them presented any example bigger than 3 states. Just so, yeah. I mean, some of them had solved with some heuristics other examples, but they never showed a plot of that or something. So 6 dimensions is what some people say is possible. But yeah, probably not very complicated ones. So I just wanted to say this is definitely limited, and since decades it's limited. Yeah? So maybe it was 4 like 20 years ago. Now it's 6. Good. Still, there is one important special case where we can directly apply it. That's the LQR. Again, no, maybe I shouldn't call it LQR. I just say linear quadratic problems. And we can directly apply everything that we did before. So now if we would have a quadratic cost here, if this would be a quadratic, and we actually, I think we don't learn so much. I will just say if we would have a quadratic cost, yeah, and if you start with a quadratic terminal cost, of course it will remain quadratic. And you could now, actually there would be 2 ways to derive what I just did. I mean, one would be to just put in the quadratic terms into this equation, yeah. The other one would be to do what we did already in discrete time, introduce the same trick that we did here with an h, and then just take the limit with h to 0, and then at the end you will get at a differential equation for the matrix P. You remember J of x and t will be given by something that is x transpose P of t times x. That's what we would assume, right? That was our solution approach, which was fortunately valid in case that we have linear quadratic problems. And I will not state the linear quadratic system itself, but maybe it's ax plus bq, and so this is the f of x, right? And the L of x and u is x and u transpose QRS transpose x and u. So these are the data of the problem, and the terminal cost, I think, E, I will directly identify with x transpose P n x. And, now PT, because it's at the last time. Yeah? And after doing a bit of algebra, which I think is tedious here, we would just say, actually we can solve it by a matrix reverse equation, where we say P of t is equal to this terminal cost, PT, right? This is now a matrix, of course. It's a much easier thing than requiring this, but it's the equivalent of it. And then for basically t, being equal to t, and then down to t equals 0, so you go, so to say, down, of course not in a loop, but in continuous time, you get a differential equation for the p. And this differential equation I will just write down. So it's this q here, plus some terms which are related to the PA plus A transpose P. So I will not derive it because I think it's tedious and we don't learn too much from it. So here we put S plus B3 P transpose, and the interesting thing is here we have an R to the minus 1, just this R here, plus B transpose P. So we get a matrix equation that shows how the development of the P depends on all the problem data and on the P itself. If it would only be here and here, it would be a linear matrix equation, which we remember, but the nonlinearity comes here, and here there is a P that appears twice. So this equation you could now simulate backwards, even with an ODE solver if you want, and then you would get the terms, the function P of t, and with it you know that you have solved the Hamilton-Jacobi-Bellman equation for this specific form. Just to plot it pictorially, so what we will get here, you have time here and x here, you will get, so to say, this is a bit funny because there's a third dimension in my mind. So basically you propagated quadratic functions. Yeah? And I should say that I think no, it's all correct, sorry. So because of the fact that my cost is 0 at the origin and also my system can stay at the origin, right? So there is actually one point where all these cost functions have a 0 point, and so they would look like this, right? They all will have a different shape due to this P. I mean, the P will be different at every time point, but it will actually represent a quadratic function in a possibly very high dimensional space. Okay, so this is what you can do for linear quadratic subproblems. Are there questions for the linear quadratic case? I mean, they are supposed to be easy, because it's easier than that. You could just plug everything in. I mean, I can take the Hamiltonian here, define it, right? It will be this term plus that times a lambda, and then I can use this expression to compute the gradient, plug it in, and then all these matrices will turn up. Then I minimize with respect to u, and then somehow this r to the minus 1 will pop up, and at the end I will be at this equation. I will not do it in detail, because it's actually not adding much for the discrete time case. The algorithm, at the end you would discretize this equation actually in of integration steps, right? But it's a different equation that's maybe interesting to keep in mind. Maybe one thing I should also still say is what is the feedback control that you get, U star, which would now be, before it was a function of the index and of the state, right? Now it's a function of the state and of the time index, which is now a continuous part, so I write it like comma t here. And it will be something like a K matrix times X, right? But this K matrix is given by the expression that is here actually. So it's R to the minus 1 times S plus B transpose P. Yeah. So this is the optimal feedback control that you get here. Yeah, and then, I mean, this is just, so to say, what we did already in discrete time for dynamic programming. There's another thing we could look up, and that is an infinite horizon. So let's look at infinite horizon problems. If we have an infinite horizon problem, we would just say we have a problem where we have infinity as the end. So our trajectories live from 0 to infinity. We have our cost. There is no terminal cost because it's anyway until infinity, right? And then here we have our constraints. And the system dynamic constraint, of course, holds for all t in 0 to infinity. So of course this is in principle not always solvable. It could be that these costs grow to infinity and so on, right? But if it is solvable, there is a question.
Sorry, just one thing where
yes.
in chapter 11.
Sorry, yes. Thank you. That's a very important thing. You might get completely confused otherwise. Yeah. So on the infinite horizon, you would say if something exists, then of course if I move like one time step forward or 10 days forward or even 100 days or 10,000 years forward, the cost to go function should be the same. I mean, if it's finite, then it should be the same, and otherwise it's not defined, right? So what we will actually require is that the cost to go function, actually the optimizing value of this whole thing, right? This is what we could define to be j of x. of x0 bar. Yeah? So the optimal cost of this problem. And this cost-to-go function will, of course, satisfy the Hamilton-Jacobi-Bellman equation in a time-invariant manner. So we can actually either use this form or that one. I prefer this one. So we could actually just write down, it should be a stationary equation. So the minimum of this Hamiltonian with respect to x, nabla xj at the same point x and u, this minimum should be 0 everywhere for any point. So this is, of course, a partial differential equation on this value function j. It doesn't contain a time derivative anymore because now it's a stationary equation, and this could be called actually the stationary Hamilton-Jacobi-Bellman equation. And one can try to solve it, and of course it's difficult to solve it in the general case. In the case of LQR, yeah, for linear quadratic problems, you can easily solve it. You could just say, okay, I need to find a matrix that satisfies this equation. This should be equal to 0. And then for LQ, you will get a so-called stationary or algebraic Riccati equation, and this algebraic Riccati equation, if it has a solution, this solution gives you the optimal feedback gain, which is still defined by this equation, and that will give you the linear quadratic regulator LQR in continuous time. Maybe it's a matter of taste which way you want to go in a real application. If you have a linear dynamic system, you could actually easily derive first the continuous time LQR, and then you already have your feedback gain, and then you could be done. Of course, when you implement it, you will probably implement it in a feedback controller anyway with the sampling time. So at some point you will have to discretize, but because this function is like u star is equal to like a matrix times x, this matrix will basically be the same if you do it in continuous or in discrete time. I mean, up to little discretization errors which vanish when you have h going to 0. So in that sense, also this didn't add much value to practical optimal control. Yeah? I just wanted you to know about it. So there is a continuous and a discrete time version of everything in dynamic programming. And in the continuous time case, things get sometimes more beautiful, sometimes a bit easier to write down, but sometimes also much more tedious and more involved to prove things. And I think this is maybe enough of theory for today. What I want to do on Monday is to introduce you to something that is based on the notation that we have used here. It's in particular using this Hamiltonian function, and I want to derive basically a necessary optimality condition that should hold at the trajectory of an optimal solution. So we did that already sometime in discrete time. That was less common, but in continuous time it's actually something that is very widely used and leads to the indirect approach. Maybe to give you already, so to say, a bit of the idea, just to warm up, when we have the value function, I mean, it's here for the linear quadratic. In the more general case, it's some function. I always imagine some valley here, right? So could be a valley, could be something else, but anyway, the optimal trajectory itself will lead somewhere in this landscape. And on this optimal trajectory, I mean, the one that really starts at x0 bar, we will be able to establish some conditions that hold along this trajectory, and they will lead to some differential equations that indirectly characterize an optimal trajectory. And that way we will get some computationally more attractive tools to find optimal trajectories, which lead at the end again to root-finding problems. So that will be the indirect approach, and so please remember what is the Hamiltonian, because we will use the Hamiltonian in that chapter again. And afterwards we go to the so-called direct methods, which are the ones that we actually will understand very quickly because they build on the first part on discrete time optimal control. Okay, for now it's enough. I thank you very much and I look forward to meeting you on Monday.